Okay, very well. After this introduction, we are ready to begin. Hello to everybody. It is my pleasure and honor to introduce Professor Robert Berman, our speaker right now. Professor Berman is the professor in the Department of Mathematical Sciences at Chalmers University of Technology in Sweden. At this same place, he completed PhD in 2006. After which he spent a year and a half at the Institute Fourier in Grenoble with Professor Jean-Pierre de Mailly before moving back to Sweden. After that, he took a research position at Chalmers and now he's a full professor. Berman had several major research grants, including an ERC starting grant and a Wallenberg Academy Fellowship. And he's also a recipient of the Wallenberg Prize, the Tage Erlander Prize, and the Göran Gustafsson Prize. And he's an elected member of the Royal Academy of Sweden since 2016. So, Robert, the floor is yours.
Okay, thanks a lot. Thanks a lot for the invitation. So I will share my screen. Let me see. And then unfortunately, let me see. It seems that my picture, my video will go away from my iPad, but let me see. Yeah, so anyway, so so if, I have a pen, so I will be able to write if there are any questions. Okay, and please do ask questions to interrupt me if possible. Okay, so let me start by giving some motivation. So let X be an n-dimensional complex projective algebraic variety that I assume is non-singular for simplicity, and also assume that the canonical line bundle is positive. So unless you're a complex geometry, maybe that does not make much sense. So let me just very briefly say that I think of X as being just cut out by a bunch of polynomials, say in Cn, complex space, and then we compactify that in complex projective space to get the complex projective algebraic variety. And then, you can basically classify those varieties according to properties of the canonical line bundle. So the canonical line bundle is the determinant, that is the top exterior power of the cotangent bundle. And you can sometimes assign a sign to the canonical line bundle. And I would start by looking at these varieties whose canonical line bundle is positive, because in some sense they are the simplest ones. And by the Aubin-Yau theorem from the late 60s, these varieties admit a unique Kähler-Einstein metric with negative Ricci curvature. So that's a solution to Einstein's equation, Ricci curvature constant equal to -1. But since we are on a complex manifold, we also ask that the solution be the metric be Kähler. So that's a compatibility condition with the complex structure. And then there is a unique such Kähler-Einstein metric. So, the very basic case is when you look at the complex curve, say embedded in P2, and then if it has sufficiently large degree, so larger than 4 at least, that means that it has at least genus 2, then there is a negatively curved Kähler-Einstein metric. That's the classical metric induced from the Poincaré metric when you uniformize it. Okay, so that's the very classic situation. Okay, and basically, so why would you care about Kähler-Einstein metrics? The point is that they are really canonically attached to the variety. So if you want to study your variety using differential geometry, this is the sort of metric you want to use because it's canonically attached and somehow it knows a lot about your variety. That's the philosophy. But the problem is that this is really an abstract existence result. So it's really hard to write down, for example, some explicit formulas. There are extremely few cases where you can do that. So even the case of a complex curve is more or less intractable. Because if we would like to really understand, write down the metric explicitly, that's basically equivalent to finding an explicit uniformization map. from our complex curve to the upper half plane modulo some finite discrete or some discrete group. Okay, because if we find such an explicit map, we just pull back the Poincare metric, and that will give an explicit formula. So there are a few special curves we can do this, and that really goes back to the classical works by Weierstrass, Riemann, and all these guys. So, for example, modular curve, the Klein portic, there are a few curves where you can do this, but that's really rare. Okay, so since the problem is really tractable, let's look at the relaxed problem. So can we find some canonical Kähler metrics omega k approximating the Kähler-Einstein metric? And what we would like is that these metrics omega k are explicitly encoded by the algebraic structure of the variety somehow. So that's the relaxed problem. Okay, so let's make that a little bit more precise. What we would like is that the canonical approximation omega k should be encoded by the canonical ring of X. So this is the canonical algebraic structure, the ring attached to X. So you get it in the following way. So the point is that, we have the canonical line bundle, okay, and then we can look at tensor powers of the canonical line bundle. I write that additively, like so k times kx. And for each k, this is a finite dimensional vector space. We have a finite dimensional vector space of global holomorphic sections of this line bundle. And the condition that kx is positive actually means precisely that I can embed x in such a way that I can identify this space at level k with just polynomials of degree k. And then when you form this ring, this is just a standard polynomial ring. But the point is that you can really define it abstractly in this way, so it's canonically attached to X. Okay, and that's the sort of algebraic structure of X. And so what we want is that at level K, this approximation at level K should be encoded by the degree K component. So that's this vector space of global holomorphic sections of the Kth tensor power. And classically, these are called pluricanonical forms of degree K. So why is that? Well, this is because if you would write down such a section explicitly in local holomorphic coordinates, like here, it would just be a holomorphic function, fk of z, and it would transform as the kth tensor power of the local holomorphic volume element, dz. Okay, so that's why it's called a pluricanonical form. This is the way it transforms. Okay, so these guys are really canonically attached to the variety and want to use them to understand the variety. Okay, so here I will explain a probabilistic approach to Kähler-Einstein metrics that does lead to a canonical sequence of Kähler metrics omega k, which are algebraically defined this way, approximating the Kähler-Einstein metric. So that's what I want to explain. Okay. Okay, so the starting point of this approach is this really basic fact in Kähler geometry, that the Kähler-Einstein metric on X can really be recovered from its volume form. So that's a bit surprising if you think of it in terms of Riemannian geometry. How could you reconstruct a metric from its volume form? That doesn't seem to make much sense. It seems to be much less information in the volume form. But the point is that if you look at the Kähler-Einstein equation, what it tells you is that basically in terms of the volume form, it tells that you can get the metric from the volume, but just writing down the logarithm of a local density of the volume form and taking the complex Hessian of that, that's now a complex Hermitian matrix, and you can identify that with a metric. So this is how you get back the metric from the volume form, by just differentiating the log twice. Okay, so that's good. That means that we can really focus on the volume form, try to reconstruct the volume form, because then we easily get the metric as well. So that's what we're going to do. We're focusing on the normalized volume form of the Kähler-Einstein metric and try to reconstruct that from the algebraic structure. Okay, so what I will do is I will explain that there's actually a canonical way of choosing configurations of endpoints on X, so at random, so that we get equidistribution of these points almost surely towards the volume form of the Keller-Einstein metric. So very concretely, what that means is that I will explain that there's a canonical way of just sampling point, just throwing all these points at random, and then they will sort of microscopically, for a large number of points, almost surely approximate the Keller-Einstein volume form, like in numerical integration, for example, but without using the metric as an input into the construction. Okay, so to choose configurations of endpoints at random, what I need to do is that I need to define a canonical probability measure, DPN, on the n-fold product. It has to be symmetric because I just want to choose configurations of points without taking order into account. And as I said, we want it to be encoded by the canonical ring. More precisely, at level K, the approximation at level K should be encoded by the pluricanonical forms at level K. Okay, so to this end, I will take the number of points, not to be any old sequence of points, but it will actually be n will appear as nk, which is the dimension of the space of global sections. So what I'm saying is that I will not be able to choose any old point, number of points. The number of points will somehow be quantized by it will only be possible to choose nk points where k ranges from 1, 2, and to infinity. Okay, that will come out of the construction, even if it seems a bit odd. Okay, so what I want to do is to define a probability measure on this space here, the n-fold product, where n will always be nk. Okay, so the strategy is extremely simple. So to build a probability measure on the n-fold product, what I do is that I take a basis in my vector space of pluricanonical forms at level K. And naively, what you would do to get the a measure on the n-fold product is that you just multiply these together, evaluated at different, the value at x1, the configuration x1 to xn is just, so you just take alpha 1 of xa times of x1 times alpha 2 of x2, blah, blah, and then multiply all these together. First, you try to build your probability measure, but then I will actually do something a little bit more complicated. So I will anti-symmetrize this completely. So it becomes a sort of a determinant thing. This will be important later. Okay, so when I do this, I still don't have a measure because I really need this to transform as a measure. And if you remember, these things transforms as tensor powers of sort of dz's. So what I do is that I just take a kth root of this object to get rid of this k somehow. Okay, I call that form alpha. That's now actually an algebraic form on X transforming as dz in each variable. So it's sort of holomorphic and transforming in the correct way. But I want to get the measures, that's a real top form. So I just take the wedge of alpha with alpha bar and then some power of I to make this real. Okay, so this is now actually an honest, positive, real top form on the n-fold product. And it's actually symmetric. So that's the good, I use the determinant, which is anti-symmetric. But then when I have a bar, I get an absolute value. So this is now actually symmetric. Okay, perfect. So I will define my probability measure as just this form alpha, wedge alpha bar, and then divided by the total volume of alpha, wedge alpha bar, because I need to normalize to get the probability measure. Okay, that's the really simple construction, how I built my probability measure from a basis in this vector space of dimension nk. Okay, but then is this construction really canonical? So in other words, is this probability measure really independent of the choice of basis? That's an important point. And yes, it is, because that's the good news when you're using a determinant. Because if I would change the basis in this vector space, you can just see that my determinant construction will just differ by some multiplicative factor, which is independent of the points, because this will just be the change of basis, the determinant of the change of basis matrix in this vector space. And because my probability measure is defined as at some point I divide by the total mass, this constant goes away, you see? It comes up in the numerator and the denominator, and that's why my probability measure is really canonical. Okay, to sum up, I've built my probability measure from these pluricanonical forms. So I have my canonical probability measure on the n-fold product. And here's the main theorem, that this really reproduces the Keller-Einstein volume form. So now I can sample points using this probability measure. So each time I get the configuration of n points, I just look at the discrete Dirac, normalized Dirac measure at those points. That's now a measure on X, which is discrete, and it's a random measure because I choose my point randomly with respect to the probability measure. And the theorem says that this random measure on X converges in probability towards the volume form of the Keller-Einstein metric. So actually the theorem, the proof actually gives something much more precise. It shows that the probability that this discrete measure deviates from the Keller-Einstein volume form by some epsilon actually is exponentially small when n tends to infinity. So, okay, just to pause a bit. So this is a bit like think concretely what you would do in numerical integration. You have some measure, some volume form, and you want to really approximate it. So you would try to distribute some points on your manifold, and then approximate your volume form with this cloud of points. Think as if you put some discrete measure at those points. But the point here is that, I can do this without actually using the volume form itself, which is non-standard if you think of Monte Carlo techniques. So I don't put the volume form into the construction. I have some other way of choosing these points at random, somehow algebraically, so that I actually reproduce the volume form emerges in the large n limit. So that's the point, somehow. Okay, so this is something I proved quite some years ago, and I want to tell you about some more recent developments I've been working on. Okay, but before I do that, let's try to make this a little bit more explicit, because I said that one motivation was to actually get some canonical approximations of the Keller-Einstein volume form, or the metric. So what I do is that I have this random discrete measure on X, and I can take the expectation of that measure. So that's the sort of average measure, discrete measure I would get by sampling points over and over again at level K. So that will actually, for a large n, that thing will actually be a canonical volume form on X. And the previous theorem implies that that canonical volume form converges towards the Keller-Einstein volume form. Okay, and you can think about this in a way which where there is no probability at all. So let's think about it in a slightly different way. We're interested in X, and we want to find some canonical volume form on X, which is fairly explicit. That's our goal. But that turns out to be hard. So what we do is that we go to the n-fold product of X, space over X in my picture here. And there it turns out that I can actually construct by hand something really concrete in terms of the algebraic structure and get some canonical measure on the n-fold product. And then I can just push forward that measure to X. That's actually what the expectation does for you. And that pushing forward means that I integrate away all but one variables. And this is how I actually get the canonical volume form on X itself. So it's explicit in the sense that the integrand is explicit, but actually doing the integration is, of course, highly non-trivial and impossible in general. That you would have to do by some Monte Carlo technique using your probability measure. But somehow it's a bit like the same philosophy that you solve a linear PDE using some Green's formula. The Green's kernel is usually explicit, but then doing the integration is not, I mean, something you can do explicitly usually. So this is something like a Green's type formula for this nonlinear problem. That's the way I think about it, at least. Okay, so these, now we have a sequence of canonical volumes formed, but I promised you to get the sequence of canonical Kähler metrics. But this we can do by this standard thing in Kähler geometry. I have my volume forms. I take the logarithm of that, and the DD bar, the complex Hessian of that, will actually define a Kähler metric in this case. And the convergence at the level of volume forms actually imply convergence of these canonical Kähler metrics towards the Kähler-Einstein metric. So that's something which comes out of this probabilistic result. But to actually write down omega k, you don't really need to think of probability in some sense. Okay. Okay, so now let me move on towards Fano varieties, where I have some new results that I want to tell you about. So now we are going to consider the opposite case where the anti-canonical line bundle is positive. So that's the dual of the canonical line bundle that I write in terms of additive notation as minus kx. Okay, so in this case, a Kähler-Einstein metric, if it exists, actually it must have positive Richard curvature. So the basic case is the sphere, the Riemann sphere, for example. But in this case, it's well known that there are obstructions to the existence of a Kähler-Einstein metric. And the Yaotian-Donaldson conjecture, which is now a theorem, says that X admits the Kähler-Einstein metric if and only if this Fano variety X is K-stable. So this is an algebraic geometric GIT type stability condition. But I won't go into that here because I want to explain how to think of this from my probabilistic point of view. Okay, so let's try to repeat the probabilistic approach in the case when minus kx is positive. Okay, so let's first recall how we did it when kx is positive. So I define my probability measure as this canonical form, the alpha, which is the kth root of the determinant wedge itself, and then normalized. And I built the determinant from the space of pluricanonical forms. Okay, but that will not work for a Fano manifold because minus kx is now positive, kx is negative, and these spaces are all trivial. There are no global holomorph. There are no pluricanonical forms. So what we need to do is just formally replace k by minus k everywhere. So instead of working with pluricanonical forms, I work with anti-pluricanonical forms. They are sections of the minus, the tensor powers of the minus canonical line bundle. So sort of multi-holomorphic vector fields somehow. Okay, so we can do that. I can work with those spaces. But then in this definition, I will have to change k to minus k. Otherwise, this form will not, this probability measure will not transform in the correct way. It will not be globally well defined. So basically the message is that just everywhere we had a k, we just replace it with minus k. Okay, so let's do that, why not? So now nk, the number of points, will be the dimension of this space. And that thing will go to infinity. So I just define my canonical probability measure by replacing k with minus k. Very good. In terms of my form alpha, which is the kth root of the determinant, I'm now looking at the inverse of alpha as a density somehow. Okay, but now comes a new phenomenon, because in this case, when I normalize with this normalizing constant, there is no reason that this should be finite. This integral could very well be infinity, because now the integrand is actually singular along the divisor, the hypersurface, cut out by the zero locus, by alpha. You see, because of this, I'm using a minus sign in the exponent, the integrand will blow up along some hypersurface. And then when I integrate this, there is no reason that this should be finite in general. It could be too singular to be finite. Okay. So that seems bad, but it's actually somehow something we can turn to our advantage, because we are expecting some obstructions. I mean, there has to be some obstructions to constructing Keller-Einstein metrics. So maybe this is actually equivalent to the obstructions known from Yaotian-Donaldson conjecture, the Yaotian-Donaldson conjecture. So my main conjecture now, which is a sort of a probabilistic analog of the Yaotian-Donaldson conjecture, is that if we assume that the normalizing constants are finite for a k sufficiently large, that means that my probability measures are well defined. Then my conjecture is that X will actually admit the unique Keller-Einstein metric. And moreover, this equidistribution result I had before will still hold. So I will be able to reproduce the volume form of the Keller-Einstein metric. Okay, and conversely, if X admits a unique Keller-Einstein metric, then the conjecture is that the normalizing constant is actually finite for k sufficient large, and hence we can reconstruct the metric. So I think of this finiteness of the normalizing constant as a sort of new type of stability condition as compared to the Yaotian-Donaldson conjecture. Okay. Okay, so let's think a little bit more algebraically about this integrability condition. It looks analytical in nature, but it's actually of a purely algebraic nature, because in terms of the standard notions of birational algebraic geometry, if I look at the Q divisor cut out by the kth root of the determinant, so that's now a divisor in the n-fold product. The integrability condition means that this divisor has mild singularities in the sense of birational geometry. So it means that it actually defines a KLT divisor on X. So that means if you have background in algebraic geometry, that the log canonical threshold is strictly bigger than 1. So I will not go into, the algebraic definition. I'm just telling you that this analytic condition is actually equivalent to this algebraic condition of having this. But let me say why this point of view. Because analytically, to define the log canonical threshold of a divisor cut out by some section alpha, you just form this zeta type function zeta of beta, where you integrate your alpha to some power beta, and you you just choose some volume form and some norms, so you can integrate this. And this is obviously convergence for beta positive, but for beta negative, it will not be convergent if beta is sufficiently, if really negative. So you think of this, you start beta positive, this is convergent, and then you go down the negative axis and eventually hit the first pole where this diverges. And that's the minus of the log canonical threshold. And you can even think of beta as a complex variable. So it's well known that this zeta type function of beta is actually, it has some rational poles. And the first pole, the minus of the negative of the first pole, is the log canonical threshold. And the reason this is relevant for this probabilistic setup is that, if you remember, we really want to set beta equal to -1, because we desperately need this normalizing constant to be finite. And in my setup, this normalizing constant is this zeta function evaluated as by beta -1. So I need the poles to appear later on somehow. Okay, right. So you see, I fix some volume form on X, just some auxiliary volume form. Then I can form this beta function using some deduced norms. So alpha n is the kth root of this determinant thing. And you remember, I need to set beta equal to -1. So now here's my theorem, that I get equidistribution towards the Keller-Einstein volume form if this zeta function is finite for beta, not only beta equal to -1, but I want to go slightly below -1 with some epsilon. And I not only assume that the normalizing constant is finite, I also assume that it grows multiplicatively with respect to n. Somehow it grows like some constant times to the power n, which is the sort of natural thing to expect because we have n factors over which we're integrating. Okay, that assumption alone ensures that the normalizing constant is finite, and that actually implies that there will be a unique Kähler-Einstein metric already. But to actually be sure that I get convergence towards the Kähler-Einstein volume form, I need an extra condition, not on the poles of this zeta function, but actually on the zeros. So my hypothesis that I need to prove convergence is that there are no zeros in some epsilon neighborhood of the interval between -1 and up to some positive number. So I somehow, we know that, it's obviously along this line, the zeta function is never 0 because it's actually positive, but I need some whole neighborhood independent of n where there are no zeros. Okay, and then I can prove convergence. And basically the reason that I can do that is actually by doing some analytical continuation to beta positive, where I can prove convergence by this previous theorem, and then by some analytic continuation argument showing that actually implies convergence down to beta equal to -1. That's the way I prove this. Okay, so that's a bit intriguing, this condition of on the zeros of this zeta type function, which I need to prove convergence towards the Kähler-Einstein volume form. So let me just say some final comment about that before finishing. So this condition of being zero-free actually depends on the volume form. So remember, in this condition here, when I form this zeta function, I choose some auxiliary volume form. I can take any one here. This is just a condition to ensure convergence towards the canonical volume form. But I pick some volume form that induces a metric as well. And then I form this, this function of beta. But we are free to choose any volume form actually. And the first point actually already implies that there is a Kähler-Einstein metric, a unique one. So why not actually choose the Kähler-Einstein volume form when defining this beta function? That we can actually do because this is just some auxiliary condition to prove convergence of something which is independent of the metrics. So the hope is that if I choose maybe the Kähler-Einstein volume form, maybe this zero-free property is easier to prove. So then I have a much stronger conjecture or hypothesis, or well, it's conjecture / wish thinking, is that for the Kähler-Einstein metric, when you write down this zeta function in terms of beta, my conjecture is that when real part of beta is strictly bigger than -1, that's the region we're interested in, there are actually no zeros at all. So I really just need there to be a zero-free region here. But my conjecture is that for the Kähler-Einstein metric, there are no zeros at all. So it's much stronger property holds. And this is, so there is some evidence for this, but it's more of a wish thinking. But one evidence is that it's based, I can compute this in basically on Pn, the simplest case on Pn. And in that case, it turns out that this really gives this zeta function is really a local L function. We can identify it with a automorphic local L function, and that thing is manifestly always non-zero everywhere. So the hope is that somehow zeta functions in general, by some deep reason that I don't understand, but hope exists, that they are actually always non-zero, just like all L functions, local L functions are always non-zero. So I think I will stop here.